First, I should thank Dr. Ben for his introduction, and also want to thank all the audience and also the invitation from Professor Gani. And today I will give a talk about the mobile network beyond 5G and a little something about my previous research and the current study of the 5G or beyond 5G about the mesh network, vehicular network, and the air, space air vehicular networking. So for the screw. Okay, so I will give a short self-introduction as well, and furthermore, I'm going to talk about the multi-hop networking and the air-ground networking, and also I will talk about the future networks and some information about the future networks. About myself, and I was introduced by Dr. Ben, and my research interest include vehicular networks, space air-ground networks, and the mobile edge computing, which is also called MEC. I have authored and co-authored some papers, and some of them are actually transactions and European journals. And I have applied and granted of more than 40 patents and two edited chapters and one monograph. And for the research activities, I have act as program co-chair for the HOP IUCC 2019 and the publicity chair for the ScaleCom 2020 and some other conferences and workshops. And I'm also just from last month, I have acted as a member of the HOP INGR, here I listed INGR Satellite Working Group, which is a working group for the satellite ground communication and networking. So I am an active member in that working group, and I will work in this area for the future of the 5G and beyond 5G or 6G technology. And for the guest editor job, I have act as the lead guest editor for the HV transactions on network science and engineering and some journals, some well-known journals. I have supervised some MPhil students, including Chinese and overseas students in my university. So it's just a short introduction about myself. And for the future network, so-called beyond 5G or 6G, and we have a roadmap from the HV future network. This is a organization, sub-organization of the HV, and we can see that there are some examples of the applications can be held for the 5G and beyond 5G, like the media and education applications, and here I wrote the predictive policing and like the mobile healthcare via the wearables and which the industrial IoT, which industrial Internet of Things and autonomous manufacturing. Sorry, I have a typo here. Are also the key component for the beyond 5G or 6G, and we will also going to see the smart agriculture and the environment monitoring for the 5G and the beyond 5G. So what we need to have is for the beyond 5G compared to the current 5G standard, right? For the beyond 5G and the 6G, and we need a ubiquitous intelligent connectivity and the computing to realize the above applications, right? So because the current number of the we can see that the current cellular technology required the construction of great numbers of infrastructure, and for example, the base station in 5G in the current standard For example, as an example, I can say that China needs 20 millions of 5G base stations to cover all the outdoor areas in the Chinese in the China homeland. So it's a lot of base stations. It's cost. And for your information, for the 4G base stations, there were like 4.4 millions of base stations have been built in the past 10 years in China. So it is a great number. So it costs a lot of money to build this, to construct this infrastructure, and to buy all the base stations, right? And so we need a lot of money to keep the maintenance of the infrastructure. And for this reason, we need to find alternative solution in the future technology promotion, and in order to realize the ubiquitous connectivity. So first, we can see that we need to have the multi-hop networking. We need multi-hop networking, and is one of the potential solution. And second, the space air ground networking, such as like the interesting SpaceX, can be another potential solution to provide the wide area communication and the networking. Okay, so let me first introduce something I have done in the last 10 years. The first thing I want to introduce is the wireless mesh network. So it's short for WMN. So it is designed to provide the metro area broadband access. So back to like 10 or 15 years ago, this networking architecture is very promising. It was a very promising technology to enable the broadband connectivity in less developed area, such as Africa, the African countries. So it has some attractive features, also called characteristics, including the low capital cost, low power consumption, self-configuration, and organization, high integration with other networks. And also it has a great characteristic like easy installation. So for the WMN, it aims to provide connectivity to low mobility nodes, such as you can see that there is a example in this figure, right? This example in this figure. It's normally to provide the community, the broadband to the community, like this, a neighborhood, right? So we use the internet. We can just build the internet backbone, right? We use to get the internet gateway to connect the internet backbone by the wired links, right? So then it has three layers. So the internet gateway layer, the mesh layer, and the client layer. So for the gateway layer, it has all the internet gateways, as you can see from the figure. And for the mesh layer, it has all the mesh routers like this. Like it's just like the base stations you can observe from our current 5G or 4G standards. And we also has all the clients in the client layer. So we can see that the mobile phones and the houses, and the low mobility persons, human beings in the community. So this is the basics architecture for the wireless mesh network. And here is one of our previous work published in the IEEE transactions on power line and distributed systems. And we have proposed one new multicast routing algorithm, so-called GMR, right? So it's short for Gateway Multi-Hop Routing Algorithm, where the GMR shifts the role of gateway from a simple packet forwarder to a routing orchestrating node. GMR is like you can see that GMR is a hybrid routing in both proactive and active components cooperate concurrently. So this makes GMR very suitable for the implementing on a variety of different networking configurations. So as we can see that the mesh network is a low mobility network. So we can have the reactive component of the GMR to handle the high mobility nodes. So the high mobility nodes are just a small portion of the whole network. So okay, the whole network. So like some cars, I didn't draw it in this figure. Some cars, but most of the nodes are like the cell phones, cellular phones, and the houses. All right, most of other nodes. These nodes are low mobility, so we can use the proactive part component to handle the low mobility nodes in the domain. So in this work, Open GMR, novel multicast gateway multi-hop routing algorithm is also proposed to handle the high bandwidth applications. So we can see that the multicast is very important in the in the scenario of the networking. So the multicast is the combination from to send the information from a group of nodes to another group of nodes, right? By awarding the replicating of the messages. So normally we use multicast like to multicasting the video program or audio program. So it's very bandwidth consumed. So unlike the existing work, the MGMR, which is the multicast version of our proposal, considers the QoS, with quality of service promising, and load balancing, and the capability of the gateway-based management in this large-scale network. So we all know the multicast is complicating, so we can use this newly proposed solution to minimize the bandwidth consumption and to maximize the packet delivery ratio and to reduce the delay. We can see that from our excuse me, from our results, right? Here are some results of the proposed solution. Excuse me. We can see the MGMR is compared with the other well-known multicast routing algorithms, including MAODV, ODMRP, GLBM. So these are very popular multicast ad hoc routing algorithms back to 10 years ago, right? So we compared with them in terms of latency, right? Latency, throughput, and packet ratio in different sized of wireless mesh networks. Here I wrote WCN, where WCN is short for wireless community network. So wireless community network is the type of mesh network. Is just to particular to provide the connectivity in the community, in the neighborhood. And we can see that our proposed solution outperforms other existing solutions in terms of this, right, in different size of the network. Okay, so here is another work, right, we proposed for the mesh network, right, for the multi-hop mesh network. Since we have the different communication demand for the for different applications, actually we can see that the applications of mesh network act the same. I mean, the back to 10 years ago, all the solutions they consider that the applications act the same. They have the same demand, but in fact they have different demand. Like for instance, we have those broadband TVs, right? They consume a lot of bandwidth, and they require real-time communication. But like, for example, the web page browsing software, like web browsers, they just don't need the real-time communication. Sorry, excuse me. They don't need the real-time communication. They just need the like non-real-time, and they don't need like high priority for the transmission. And for this purpose, right, we propose two routing metrics. So the routing matrix, maybe some of you don't know what is routing matrix. The routing matrix is to help the routing algorithm, also called routing protocols, to find the most proper node, next hop, right, among in the neighborhood. And we propose two routing metrics, and the one is called priority oriented routing metric, PPO, and the other one is called packet priority oriented QoS routing metric, PPQoS, in order to enhance the QoS of the mesh network. And so, as different to other work in the in the mesh network, and our algorithm considered the different communication demands of the mesh applications, and we give the different communication priority to the applications in the mesh network. In this case, we give the higher priority to the real-time applications, and for this work, we won one best paper award in IUCC 2015, which is one in HOP International Conference. Right, here are some results. All right, so here are some results, and we compare same to the previous work. We compare to other existing routing metrics in both heavy loaded networks and the light loaded networks, right? To test whether our proposed metric is better than others. And you can see that we we use the QoS, the performance metric, including the throughput, latency, and the average end-to-end delay for the high QoS applications. So the third performance metric we want to use is just to compare, to see whether our proposed solution can give a better bandwidth and better latency to those applications with real-time communication demand. And in the heavy loaded random topology networks, we can see that for the light traffic grid topology network, we can see that our proposed solution can provide better communication quality compared with the existing solutions. And also for the random topology, we also provide the same much better performance. And so, like back to 6 years ago, I switched my research direction from the mesh network to the mobile network, which is called Vehicular ad hoc networks. And in particular, in this work, right, to realize the ubiquitous networking, the vehicular ad hoc networks, also which is also called VANET, right, is to design to provide networking access to the autonomous driving. And our team is among one of the earliest teams around the world to initiate the study of the AI-enabled multi-hop networking for the VANET. And we can see that compared to the mesh network, the VANET has different characteristics. Like you can see that in mesh network, all the nodes are less mobile. Most of nodes are fixed, right? Like the houses, whole buildings, and some very small portion of the nodes are like less mobile, like the human beings. But in the vehicle network, because we want to provide the message propagation and provide the information to the vehicles, so the network is highly mobile. And first, the size of network. The size of network is big, right? You can see that for city, there are like thousands, hundreds of thousands for big city of mobiles, of like vehicles. And as I introduced before, the node mobility, the node moving speed is very high, and the node moving like along the road network. So this is characteristic for the VANET. And the topology and the density. The topology can be changing, can be highly dynamic because of the moving speed of the vehicles. And the density nodes, the density of the vehicles can be varied during the time changes, because you can see that in the peak time and for the peak time and for the off peak, like during the night, the size of the numbers of vehicles are different in the same city. And for the hardware, there is no energy constraint in the vehicle nodes compared to the wireless sensor network. So this is all the main features for the VANET. And the selection of the next hop forwarding node in some cases is not optimal. So we propose, for these reasons, we propose one new algorithm, namely greedy machine learning routing. So by applying the machine learning algorithm, also called method, SVM, support vector machines, to improve the routing metric model in location-based greedy routing protocols like GPSR. So GPSR is an old protocol, but we use the machine learning to learn the characteristics and the behaviors of the drivers, right? So how the behavior, to learn how the behavior of the drivers can influence the movement of the vehicles, and to study how the moving of the vehicles can affect the networking quality to communication and the communication quality. So you can see the comparison, the simulation results. Our right, we just done, because it was a conference paper, just done very few comparison the simulation. You can see that our proposed solution can outperform the standard GPSR. Okay. And here is another study, right? After the study of the machine learning based VANET routing, we also studied applying the fuzzy logic for assisting the decision making during the routing of VANET. So this work published, I was the corresponding author of this work, and this work published in the IEEE Transactions on Fuzzy Systems. And so for this work, we divide routing to two processes: the intra-pass process and the inter-pass process. So for the inter-pass process, right? So you can understand that as selecting a sequence of successive road segments, right, within within the city area, right? Okay. Okay. So this is this road segment selection. Some figures. So this is the inter-pass selection, inter-pass process. And for the inter-pass process, we is modeled as a multi-objective function, and we consider multiple attributes, like including density, shortest distance. And here density is defined as the linguistic variable with 3 fuzzy sets: low, medium, high. So we're going to see that more information from the next slide. And the intra-pass process is considered as this to select the relay vehicle within one road segment. So the intra-pass is to find the sequence of different road segments, and the intra-pass is find the vehicles within the one road segment. And we modeled this intra-pass process as also as a multi-objective function. And we also consider multiple attributes, including the speed differences and the moving direction of the vehicles. These are all the standard attributes for the vehicular routing, and as well as the signal fading and the path loss and the transmission distance. Okay. We also use the fuzzy set to build to model these attributes, and to identify the relationship among captured attributes in intra-pass and inter-pass processes. We also used one AHP or analytical hierarchy process to build this, to identify the relationship between of the captured attributes, right? So you can see the next slide. So here you can see that in the middle, in the table here, I showed in here. The table shows, right, the relay vehicle selection rule base, right, which is the rule base for the intra-pass process, right. So we define the different attributes here, right, and we also have the different rules listed in this, right, in this fuzzy set, fuzzy table. Okay. So we compared, because the limited size of the presentation, I just listed very few numbers of the figures comparison results. You can see that, right? You can see that our proposed solution also improve the latency and the cost, and improve the latency cost, and reduce the delivery, reduce the overhead, and also let's say improve the delivery issue, right? To improve the quality of the communication for the VANET. So here are some more results, right? Right. Okay. So in the last few slides, I introduced the VANET, the standard VANET. But for the standard VANET, during the study of the standard VANET, sorry. Okay, I shall continue. So during the study of the VANET, we find that we can see that the standard VANET, they are ad hoc networks, so they are distributed manner. So the distributed manner can't handle the data collection, and which leads the application of the machine learning, deep learning, reinforcement learning are highly constrained, because they can't, for distributed manner, for one node, they can't collect enough information, and it is not easy to gather all the information for the learner. And also another constraint is the limited, right? Sorry, thank you for this. And this is, and another problem for the VANET is the limited hardware computation power of the end user device. You can see that the vehicle industry, for the vehicular industry, they try to reduce the manufacturing cost when they producing the vehicles. If we integrated the high costly hardware into the vehicles for the machine learning, it will increase the price of the vehicles, the cars. So the customer won't buy it. So we need a brand new architecture to handle these issues. So we propose introduce the SDVN, which is short for software defined vehicular networks. Software-defined vehicular networks, right? And it is a softwareized version of the VANET. And the SDVN is very promising vehicular networking paradigm, and to provide the extensible and flexible means to manage the networks to enable the V2V and the V2I communication. So we can see that from the feature. So V2V is the vehicle to vehicle, vehicle to vehicle. So in the current standard of 5G is only you can see that the D2D communication is V2V, but it only supports the one hop due to the cost. And the V2I is the vehicle to infrastructure, infrastructure. So with the SDV and the new routing schemes can be deployed so easily in the SDV controller. So right. So by borrowing the softwareized networking idea, the network, the newly proposed SDVN decouples the data plan and the control plan. So the control plan is in the controller here, and the data plan is here for all the vehicles. So the vehicles, the devices of vehicles will only handle the data forwarding without networking. So the cost of the manufacturing of the hardware devices will be reduced hugely in this case. And all the computation of the and the management duty, like the routing duty, will be handled and managed in the central controller, and as well as in the RSU. Maybe there are some kind of local controller here. So in this case, right, so the controller will learn the data, will gather the data first and learn the data and build the most proper, right, the most proper routing algorithm for the data plan, and they will distribute the routings, right, to the data plan, to the vehicles, and the vehicles just need to forward the data, right, in this case. So this is a better architecture compared to the fully distributed architecture like in the previous VANET. Okay, so okay. And of course, we, as a newly proposed architecture, the SDVN has its advantage and disadvantages. Like we introduced, we can refer to this table. I have listed all the advantages of and the disadvantages of different types of SDVN. First, we can divide the SDVN into centralized and hybrid, right? So for the centralized routing schemes, right, the controller provided per flow routing, right, the centralized per flow routing to the data plan, to the vehicles, right? But in contrast, for the hybrid routing schemes, it's just the controller will just make the routing policy and distribute the routing policy to the vehicles, and the vehicles will like implement deploy the routing policy in their hardware and act like the ad hoc network, like just like the VANET. You can see that for the advantage of the centralized, the advantage is efficient route, high data delivery, but it has the problem of the burden of the central controller, because you can see that for the fully centralized SDV, and the SDV controller need to collect and gather all the status data, all the information of the network from the vehicles, and there are lots of transmission overhead from the vehicles and to the controller. And for the hybrid architecture, of course, the advantage by applying the hybrid, only applying the routing policy, the uplink overhead will be reduced, and it will achieve better load balancing. But it will provide the low data delivery, because the routing are not always the optimal, because it's still a distributed manner. And it also faced another problem of the high local overhead, because compared to the uplink overhead, the burden of controller, the local overhead will be increased because of the VANET, or the ad hoc nature. And so this is the first classification, the type classification method. And we also can classify the VANET to single pass and the multi-pass. Right. So for the single passes, you can say it's only going to be one pass, and for the multi-pass, and there are some other schemes also establish multi-pass routing rules to guarantee the delivery, right? Right? And it's also going to guarantee the load balancing, and will achieve short latency in this case. And okay, so I don't think I need to hurry up. Maybe we don't have enough time. And okay, so the third we can see that third type we can see here in this table is the beacon based and the prediction based. So we can refer to the early introduction in the centralized classification, right? For the beacon based, right? For the beacon based, all the information gathered in the central controller are collected from the vehicles, right? But for the prediction based, right, all the information, some of the part of the information can be predicted in the controller, because the controller is very powerful. They have no energy constraint. They have a lot of computation power. They can do the prediction based on the historical data. So they can do some prediction, like the prediction of the trajectory of the vehicles and the parameters of the vehicles. So you can see that for the prediction based, it has many advantages, like low overhead, because we don't need to always transmit the information from the vehicle to the controller, and it's scalable, and it's very good for the dense network. But it has its disadvantages, like the high latency, because we always predict the information, the status of the vehicle according to the previous data, the historical data. So it will cause some latency. And we also have other classification methods, like the geo-based and geoless, and the sparse and dense. I won't introduce further in this guide. And if you have interested in this paper, you can refer to the paper we published in the HB ITS magazine this year. Okay. Okay. So as it is a new architecture, so it has lots of open issues, including the lack of the research dedicated trajectory prediction algorithm. We talked about it before, right? if we have the predictive-based SDVN, we need to have the prediction algorithm to predict all the information of some part of the information of the vehicles, right? Including the trajectory, which is the trajectory is the most important information of the vehicle, which the controller need to know. And the second open issue is the further reduction of communication overhead, right? So with the trajectory prediction method, definitely we can reduce some part of the communication overhead, like mostly the uplink and downlink between the controller and the vehicles. But we still need to further reduce the communication overhead in able to realize the SDVN maybe in the future of the commercialized standards. And the third is the lack of the research of the routing algorithm in the controller, right? So currently, most of or back to like this paper was written like 2 years ago, I think 2 years ago, back to 2018. There's most of routing algorithms for the SDVN, they applying the static shortest path algorithm. But we can see that the SDVN, the vehicle network is not static, it's temporal. So I will introduce one solution for this in the latter slides. And the fourth open issue is the applying of the AI, artificial intelligence, in the management of the controller. We said that the SDVN, the most important feature of SDVN is we have the central and the local controller. We have the mostly centralized control system, right? So it has powerful computation CPU. So we can apply the AI and or machine learning algorithms in the controller, because it has powerful CPU, and mostly they have some powerful GPU in the controller. So we can always consider controller as the MEC, mobile edge computing server, right? Or some type of device equipment installed besides of the base stations, right? In our future scenario. So until 2018, there was no such routing management algorithms. Yeah, considering bringing the AI technology to the. Okay, so here are two more open issues for the SDVN, including the multicast routing and the security, right? So if you're interested in this part, you can refer to the paper. So I'm going to show you the next one. Okay, so this is the future direction of SDVN. So you may some of you are like PhD students and MPhil students, I believe, and if you're interested in working on the topic in this SDVN, you can refer to this future direction figure, right? We have some future directions, right? Like how to enhance the AI, right? Build the AI, and how to do the more precise prediction algorithm. And as you can see that the AI, machine learning, and reinforcement learning and deep learning, they are among the most popular and most hot research topic in networking. Also include the networking of the vehicles. So if you're interested in the research for the vehicular networks, you can like work in this area. Okay. So here is another paper we have done, another work we have done for the SDVN, and like we introduced a hybrid SDVN already. So I want to like emphasize the SDVN with the hybrid SDVN. In hybrid SDVN, the local controller acts as one mobile edge node, as we can see that, for collecting and processing the local features, the feature data. And the central controller is responsible for merging the data and training the decision-making model in real time. So we can see that compared to the centralized SDVN, the hybrid SDVN only make the decision-making model, which is it's only a policymaker, the controller, right? And for the centralized SDVN, the controller is like a computer. It's a path maker, right? So here in this work, we published in the ICC, ICC in Shanghai, and we proposed one method first to extracting the road information from the real network, real node map, right? And then we applying the OS ELM, which is online training. It's a neural network model to train our data, right? To train our data on trunk by trunk and one by one feature nature, and so it can be used for the real-time application. So we want to train the policy in the controller every once a period, and then distribute the policy to the vehicles within one area, geographical area. So of course, there are some results for our work. Here is the peculiarity ratio and latency, right, for the small topology, because we need to test the scalability of our proposal, and then we compare our proposed solution here, right, with the existing methods, right, with existing methods within different in terms of different geographical areas. So we have a small topology results here, and we also have the big topology here. Right? So bigger topology. Okay. So here is another work, right, also published in ICC, and this work also we extend this work and submit it to IEEE TMC. And in this work is centralized SDVN. So last one I introduced, the last one ICC paper I introduced is one. The commentary. The last one is proposed hybrid, but this is centralized. So all the routing paths will be calculated in the controller. You can see that in the figure we draw is there are base stations. We consider the base stations, the controller is just installed in the base station, the local controller. So in this work, an efficient optimal routing algorithm is proposed for the temporal graph. So what's temporal graph? So in the early slides, I introduced most existing work. They consider the network, the whole network, as static, right? As static. They use the static shortest path algorithm to find the best route. But it's not right. It's absolutely not right. As we said, right, the vehicular network, they're highly dynamic, so it is temporal, right? This special temporal. So we use temporal graph to do the single source shortest path calculation. So because we want to reduce the communication overhead, we used HMM, right, hinder Markov model-based network to predict the trajectory of the vehicles. And in this work, a novel prediction strategy, we used HMM to predict the enough RES, right? This is RES is the link quality, right, among two vehicles. So the routing path among these RES can guarantee the reachability of and the delay. So we can see that with this with the proposed temporal graph. With proposed temporal graph, we can achieve better latency, right, and better packet registration, and as well as the lower jitter. This work. Okay. So as I introduced before, besides the multi-hop routing, the space air-ground networking is also one important component of the future B5G or 5G beyond, or also important for the 6G. You can refer to all the news in the recent news of the space. They launched the satellites to they will launch like thousands of satellites, like the low orbit satellites for providing the ubiquitous connectivity to the customers. So we have done some research, right, in the recent 3 years about the air-ground network. Yeah. Sorry. Excuse me. Okay. I'll continue. So we also studied the UAV assisted networking. So as one important part of the UAV networking, the UAV path planning is very important. So in this work we published in the last year, we proposed one solution for the UAV path planning. So we applying the improved artificial potential field APF method to accelerate the convergence of the best position update process. So in fact, we used the BAT algorithm to find the best path planning for the UAVs. And here are some algorithms, and we found some problems for the and the solutions for the UAV path planning. First, for the APF, the UAV path planning is defined as the process of finding a path from the start point to the end point to meet the performance requirements of the UAV under some specific UAV flight constraints. So of course we have some UAV flying constraints, such as the energy. The energy is the most important concern for the UAVs, and also we have some other flight constraint because so we use this. This is the problem. So we use the APF method to solve the problem. We improve the APF method, and to solve the problem of the path planning. This is the first one, and the second one, we also have some problem about the exploration process and the export process for our heuristic search algorithm, because we use this the APF for the BAT algorithm. BAT algorithm is one type of the swarm intelligent algorithm. So we need to like better explore the process for the export process and the exploration process. And the solution we have is we use the adaptive inertia weight-based optimal success rate transform to better enhance the global search and the local search, and to improve the efficiency of our the BAT algorithm. Next slide. And the third contribution for this work is we are also applying the choice strategy, right? So to for the initial best population, right? For the initial best population. So I won't go further for this work because due to the limited time of the presentation. So if you're interested in the work, you refer to the paper published to this computers material and continua. This is one open access paper. So okay. So another air-ground networking scheme we have done is the another thing we need to concern is how to grouping the multiple UAVs in our scenario. How to gather the UAV together, how to do the collaboration, right? How to do the collaboration, because when we want to use the UAVs to cover the area, we need the UAVs to do the communication within the group, right? And also we need the UAV to ensure that the communication security, to ensure guarantee the secure communication. And so in this case, so we proposed one other work, right? We have another work here and published in Computer Networks last year. So this work considers the communication security of the multiple UAVs, and once we need the UAVs to do the clustering. So why we need to use the UAV? Why we want the UAV to be clustered? Because when the UAV is clustered and flying together, it can reduce the energy consumptions, right, of during the flying, because it reduced the wind, the energy consumption from the wind. And the first in this work we introduced the flocking algorithm, right? We use the flocking algorithm to enable the UAV flying cooperatively and to reach one relative stable position here. This is the UAV group communication feature. And the second contribution of this work is we used one UAV dynamic model to make sure to best position the UAV trajectory position of each UAV and the velocity and the other informations. Okay. And also we use the HVCR, which is short for theoretical virtual communication ring, this algorithm to address the communication strategy. So here we can see that first the UAV group is stratified to find the boundary of the UAV of the UAVs, and then the insecure range, when the insecure range decreases, and we're going to decreasing the communication radius of this, so we can have a small we can have our UAV group gathered together as small as possible in order to reduce the energy consumption during the flight. Okay, here are some results. I skip the results. And if you're interested, you can refer to the paper from we published in communication. It's computer networks. Okay, so here is another work we have done for the UAV transmission, right? And this work, so we aim to provide the energy concerned algorithm for the multiple UAV transmission, and based on the limited time for the maximum transmission. So this is one green sustainable UAV communication model, and we convert this, or we model this as one optimal stopping problem, right? And we find optimal data energy efficiency in this work. And in this work, we reduce the energy consumption of the data transmission by using the optimal stop-based algorithm. You can see that in this picture. We also involve the UAV flocking and the communication in this work. Next. Okay. And another work we have done, this is one work we have done recently, published recently in IEEE transactions on various communications. And this work considers using the UAV to maximize the coverage of network and to enable the vehicle connectivity. We use the UAVs, right? You can see that it also borrows all the studies from the last few slides. We need them to be gathered together collaboratively, work collaboratively, and we need to ensure communication privacy and security. And we need to allow the one-to-multiple UAV communication. And in this work, we can see that we need to find the best positions to place the UAVs for the above purpose, to provide the vehicle communication. Sorry, the figure is very small, but you can see that there are small vehicles on the ground. Right? So for a certain position, we define the detailed criteria to evaluate the demand of drones, which is also called UAVs. And we consider the multiple objective of the VANET and build an evaluation function of the optimization problem. So we have 3 layers here. We have 3 layers for this architecture, for this structure. We have the lower bound is the lower layer is the VANET layer, as we introduced that, right? So for this scenario, we assume that VANET is the networks sometimes are sparse, right? Like for instance, for some cities that there are not very much of cars, or the cities without very good infrastructure. So the cars can't be connected very well. So we need the VANET, right? The VANET, the flying ad hoc network, to be formed, and the flying ad hoc network can provide the access to the VANET, right? So we also have one top layer is data center layer. In the data center layer, the data center can collect all the information within its covered area and analyze the data. It's just like a controller, but in this way we call it a data center, because for the data center, it also needs to make the path planning decision for the UAVs, because we need to tell the UAVs where to fly and which position to fly and which vehicles to cover to provide the internet coverage. Okay, so To solve the best, to find the best position to allocate the UAVs, we proposed one. It's also one multimodal optimization algorithms, namely multimodal nomad algorithm. And this algorithm is inspired by the nomadic tribes on the Mongolia parallel. And this is MNA. MNA enables the instant dispatching of the multiple drones, as you can see that, and to locate their best services to the best positions to enable to improve the efficiency. Okay, here are the results. We can see that the results were very good compared to the existing work. And if you're interested in this work, you can refer to the paper, our paper. Okay, so here are some more results. Okay, so for the future network, I believe the future network, like the future management of the human being, is going to have twin city or digital twin-like architecture. So I borrowed the idea of the digital twin and to emphasize the digital twin in the SDN, right? Because the digital twin, I believe some of you are familiar with the digital twin as one technology mostly used in intelligent or smart manufacturing. And for the digital twin, we want to build one virtual network based on our real world physical network. So why we need to use the digital twin? Because the current architecture I introduced before, the SDVM, can't fully can't fulfill the needs of the vehicle networking. Because we always need to predict, predict the information, but we can't tell which predicted or which learned algorithm or which learned policy is better than the other one. So we need to have one virtual world training and to experiment to examine whether one learned algorithm or learned solution is better than other one, and then we can implement the best solution in the real world. Right? That's why we need the digital twin, and we need the digital twin to be intelligent. So we need to implement to deploy some AI-enabled algorithms in this digital twin. So it's called intelligent digital twin. Intelligent digital twin SDVN. So you can see that we have a virtual network here. We have the physical network, right? So for the physical network, we can observe all the information, and the physical network will transfer and will send the vehicle status data and update them to the virtual network. The virtual network is built in the MEC server or controller, and the virtual network. For the virtual network, it will virtualized. It will simulating multiple network, or you can say multiple virtual networks. And for each virtual network, we can apply different learning algorithm or different parameters to learn and to examine the learned solution. So this is much better than the existing SDVM. Okay, so it can provide some services, IDT, SDVN, the intelligent digital twin, right? SDVN. First, we have the powerful data aggregation and visualization. So we can have the global view. Each a controller can collect and store the vehicular and raw data. And the second one is IDT networking. So we can refine the networking schemes time to time, right, based on our intelligent algorithm. And also, as we introduced, we can also use the IDT verification, right? Because we built the virtualized world, which virtualized the network based on the real physical network, right? So we can use the virtualized the network, the digital twin, to examine the learned network schemes, including the routing scheme and policies. And of course, compared to the SDVM, we have more opportunities of this newly proposed IDT SDVM. You can see that we can big opportunities for the learning algorithms, and we can build and learn how we can the schemes to switching from the virtual to practical. So when and how and what algorithm can be applied in the physical world from the virtual world. And the third opportunity is we also can learn how to adjust from the filters, because sometimes some learned algorithm is still not perfect. So we want to learn from the filter. We want to have the data time to time gather the data from the physical world and learn them, examine them in the virtual world. And also another open opportunity is validation of the strategy. So how to validate the virtual simulation environment, right? How to validate? Because without validation, the effectiveness of the verification on the networking schemes they are useless, because we can't say that this verification are how to say guaranteed. Okay. Okay, here is one case study of the IDT SDVN. So we applied the HMM that work from the ICC conference introduced in the early stats, and find whether we can have a better result if we apply the hidden Markov model idea in this newly proposed IDT SDVM. The results we can see that we for the virtual for the IDT SDVM provides better delivery ratio and delay, most one unneeded, and this is only our initial experiments data. So if you're interested in this work, you can refer to the IEEE network, this paper just published. Okay, so here comes on my conclusion and the future work. And here in this talk, I introduce the wireless mesh network for extending the urban broadband coverage for less developed areas. And then for the vehicular networking solutions, and I introduced the VANET, SDN, and for extending the coverage of the vehicular net communication. And because the current, we can see that the current 5G or 5G V2X can't support the vehicle's communication very well. So it will be one essential component. We can involve the UAV and the future the satellites in the study of the VANET. So I also introduced also show the collaborative multiple UAV UAV network communication, and the path planning and the UAV assisted VANET. And for the future networking, so in the last slide I introduced the digital twin, intelligent digital twin SDN. And for our future work and for our research team, we will still focus on the vehicular networking. And because I also act as one member of the IEEE standardization committee, the INGR satellite working group. So I'm going to also work on the space air-ground networking to further involve the satellites in the air-ground scenario, networking scenario, and to further enhance and realize the B5G and 6G to enable the connectivity of everything in the world. Okay, so I think this is my talk. This is my presentation, and thank you for watching the broadcasting, and thank you for your time. And yeah, any question? I think yeah.
Okay, thank you, Dr. Zhao, for the very interesting and highly informative talks. Now we open for Q&A. So the audience is welcome to ask the speaker any questions which related to this topic, especially for the network. So welcome, please.
So can I ask a question? This is Professor.
Thank you. Please.
Thank you very much for your good presentation. I'd like to know your perspectives about when the vehicular network will become widespread. At the same time, what will be the main killer application in vehicular analog networks?
So the first question is thank you for the question. And the first question is when the application will be realized, right?
Actually, when will be deployed?
Deployment. Okay.
Yeah.
I think for the vehicular networks, the current 3GPP standard is it's release 15, and for the 5G V2X, I think the current standard for the V2X is going to be based on the release 16, and even for the release 16, the most standardization material shows that it's only single hop. It's only single hop, and to be honest, our papers and our studies, I mean, they are for maybe 10 years later. But for the vehicular, for the V2X, for the cellular V2X, will be realized maybe earlier next year, I believe, because there are also some like experiments taken in China and the US and Japan, European countries. So it will be commercialized like next year, I believe. But different standards in Europe, they use DSRC, and the US they use DSRC. But for China, we used 5G V2X, the cellular solution. Most of solutions are now single hop, not multi hop, and so they can't work very well for the sparse scenario, right? So when they're on the scenario of when there are not many infrastructure, because for the cellular solution and as well as the DSRC solution, they always need a base station and all the RSU. Okay, so and the second question is, so sorry, I forgot your second question. So could I beg you repeat your second question?
My second question is, what will be the main or killer application in vehicular march-up networking?
for the vehicular, right? For the
Yes,
vehicular.
So good application needed to deploy the vehicular match-up networking. So what
Yes.
key application in
The key.
match-up? Yes, key or key application.
I will give you some applications for the future, and the most important application for the vehicular network is the autonomous driving, right? So for the current solution of the autonomous driving, mostly all the cars are embedded with the sensors, like up to like hundreds of sensors, but they are costly. They're very expensive. You know, you see that like the full pack of sensors for one autonomous vehicle may cost like 2,000 sorry, $20,000 US dollar, right? So it's very expensive. So and due to the limit of the image processing technology currently, so you see that there are some bad news for the accident caused by the Uber and Uber autonomous driving cars and Google cars and especially Tesla. They have some problem of the image processing and to recognize the vehicle, the sky, and so forth. And the V2X, vehicular communication, vehicular networking can be a alternative solution or can be a supportive solution for the autonomous driving. So this is the key application. Okay, I don't know whether I answer all the questions you asked it.
Thank you very much.
Thank you for the question.
ولو كان ذا قربى تحبسونه بالسراد ويقسمان بالله إن ارتبتم لا نشتري به ثمنا قليلا ولو كان ذا قربى ولكن شهادة الله إنا إذا لمن الآثمين فإن أصروا على أنهم استحقوا اسما وآخران يقومان مقامهما.
There are some questions from the
وإذا قيل لهم تعالوا إلى ما أنزل وإلى الرسول.
Is there somebody is speaking? Is there another question?
Hello, good morning, Dr. Zhao.
Morning.
I'm Edmund here from FI.
Yeah, nice to
I
talk to you.
would like to ask one question here. Yeah. Can you help? Can you hear my voice here?
Yeah, I can hear you.
Okay, I'm Edmund here from FKI. So I would like to ask about the so-called networking regarding the agriculture or smart farming. Yes, satellite images to detect to do all those processing. So with your current 5G networking and your experience and expertise here, any way to improve the so-called using the UAV assisted VANET or your IDT network to synchronize and to do all those processing using into the so-called agriculture?
Okay, for the agriculture scenario, I think it's very important to deploy the drones, the UAVs to do the surveillance and the other duties. And I believe the VANET, a flying ad hoc network, or the software-wise network can help the UAVs and to generate better path planning and to enhance the communication quality of the UAVs. But there is one important issue. There is one potential issue for the UAVs, particularly for the agriculture and other scenario as well. And because as I mentioned during the presentation, the energy consumption is one of the key problem for the UAVs. and the actual networking duty will how to say will improve. Will how to say will enhance the will how to say will assume more energy consumption, assume more energy in this case. So I believe that if we want to use the UAV networking in this agriculture scenario, maybe in the future we need the different multiple layer networks. For example, to involve the satellite, low orbit satellite, and to involve airship, right? Beyond the UAVs, right? In this case, we can use the satellite, the energy benefit of satellite and airship, right, to calculate, to compute all the networking needs for the UAVs. Then the UAV have no no energy consumption constraint in this case. And furthermore, we can assume that the airship they have no energy problem. So we can use the airship to charge the UAVs in this case. So I mean, you know, we are doing some research now. We just start the one study for this 4-layer networking scenario. Also called, it's not only networking, it's also involved the computation, the computing aspect, the edge computing aspect. So we want to place the edge computing, mobile edge computing server in the airship to compute the path planning, to do the charging, to manage the optimal networking for the UAVs. Right. This is my idea.
Very good input. Thank you very much. Because we are looking into the agriculture point of view, do you have any suggestion about the structure and the so-called solution of the design of the network for example, the about 10 acres or whatever acres land like that? Because if we are using the GPS, it might be up to hundreds or maybe thousands of using the GPS. So for the small scale one, how the architecture is going to look like?
Yeah, I believe the current solution for the drones in agriculture or other scenarios, they mostly they use the Wi-Fi, right? The Wi-Fi, enhance the Wi-Fi. They enhance the signals of the Wi-Fi and to enable like multiple or up to like 10 kilometers transmission range of the UAVs. But by enhancing the power of the communication range, I mean, it will assume more, consume more energy. And I suggest a better solution is software-defined, centralized solution. If we want to study some more papers, like the research papers, I mean to involve software-wise networking idea to solve the problem of the networking of the agriculture UAVs will be one promising solution. But if you say it's for the application, right now I really don't know, because it's not standardized. So if it's not standardized, there's no manufacturer will like sell such UAVs to support the better networking. So if for the application of the UAVs in the agriculture, like to better enhance the networking, I mean, like for the remote sensing and surveillance, I mean, you can consider to place some MEC servers in the field, and like MEC servers. Maybe you can do multiple MEC servers to process the capture the data images and analyze the images. I think that in this case, you will have the real-time image processing obtained from the UAVs. It will save some energy.
Oh, Thank you very much. Very great input, because the one important thing that we need is the image processing, the real-time image processing for in the farm. Later on, that we can process and get more input and for the analysis later on. Thank you very much, Doctor. I think we will contact you for more future collaboration for our project.
Okay, thank you.
Thank you very much.
Thank you.
Hi, Prof. Kashif is here from FKI UMS. Thank you for your nice presentation.
Thank you.
I would like to ask one question. In starting, you mentioned IEEE future network direction. So basically, can you give us some idea how we can involve in IEEE future networks? Because that is very important platform, future direction of IEEE. Thank you.
I mean, you mean want to involve in the working group, or you want to like find out what topics are interested and follow the topics?
Yeah, in working group as well as, and also maybe we can write some future direction things, like just now one of my colleagues said, we want to do something about agriculture relate to SDN or maybe future networks. Then maybe we can also write some notes or some directions.
Yes, they have for the future attribute future network, they have like more than 10 working groups, and just you need to first classify which working group you want to join or want to follow. And I think for me, because I'm introduced by one of my friends to the working group, and I'm not sure whether you are a member of the IEEE ComSoc or IEEE member.
Yes, I am a member for
IEEE. You're going to be a member of the IEEE, and then you need to join as a member of the Future Network. I can share the link to you later. Yeah.
Okay, thank you.
I will send just like the university to send the email to me, and I will share the link. Yeah. And they have like regular seminars, yeah, meetings, right? Now it's a virtual meeting, like every 1 or 2 weeks, right? And currently, because it's a future network, the most of our objective is to produce the next version of the white paper, but it's not, because it's future network. It's not at the phase of standardization. So maybe after 2 or 3 years, it will be reached the standardization phase, and we're going to do the standardization. As well as because I'm in one of the group working group, I'm not like in multiple. I'm not sure how other working group they attract members, how they attract members. But if you want to join my working group for the satellite, I can like invite you. I can ask for the chair first and see if I can put you as a co-worker.
Really, it's my pleasure if I will join your group. That's great.
Okay, so we keep contact.
Yeah. Thank you.
Okay, thank you.
Dr. Zhao, there are some questions in the chat box.
Yes. Yeah, I see lots of questions. I will pick some questions. First, for Nazmi. For Nazmi, he asked, would the deployment of drones in the sky cause any concerns of security, such as networking interference to EMFs as in the dense populated area and the airspace control of FAA? And how and will the global agencies approve of such applications? This is very good question. Very good question. And security is one among the most important concerns when we study the UAV drones, yeah, and the security and the safety of the because like in Europe they banned the UAVs, they banned the UAVs flying, and in some countries it's not very for example, in China, it's not very easy to arrange the flying of the UAVs in some part of the urban area, but we can arrange it. But we can see that the general aviation is one of the most promising industry in next 20 years. So the drones as one part of the general aviation. So it will the government, all the government will open the market to this area, to the UAVs and the general aviation, because it's a big cake. So the government will do that. So we don't need to worry about it, right? The stakeholder to worry about it is the industry. So only we can do is to do better research and to do better papers, to produce better paper technologies. If there is a market right in front of us, right, we can participate in and act as one active member in the market. Yeah, this is my answer. And I don't know whether I answer all the questions of Nazmi. And the other question is that the vehicular ad hoc night vehicular communication can detect the vehicular performance, but how about driver jostliness? How VANET detect that? Okay, so you can see that besides the VANET, there is a VANET is a part of the vehicular networks, vehicular communication, and the vehicular communication is a part of the, let's say, you can do this kind of classification. It's part of the telematics, right? Or info telematics, or onboard telematics. So within the telematics, there are also some other type of studies of the onboard cameras to detect the jostliness of the drivers. So this, all the, in particular, there are some applications in China. There are some applications and products from Jingdong and Baidu, JD and Baidu and Alibaba. They have some products about to detect the jostliness of the drivers, especially for the drivers for the commercialized vehicles, right? So if there is some kind of cameras and some type of application to do that, we can assume that the vehicle can collect such information, right, and transmit such information to the other nodes or to the controller if we use supervised network. So this is what I want to answer for your question. And the next question is, if someone understands the transmission algorithm, will there be an issue if there are someone have enough skill to interference to do the criminal activity? I think so. I mean, for all type of technology, if the criminal want to do something, if a criminal is if a criminal is highly intelligent researcher, and in this field, in any field, they can do some bad things. Yeah, it's not and we always want to eliminate the happiness of this type of criminal activities, but it's not very easy to do that, right? It's like the because I do not research the criminal activities in this field. I don't know whether I answered all your questions. Yeah, another question from Nazmi. Unless the hardware developed specific channels are not known. Okay, I think the hardware, because when we design the algorithm, certain algorithm, we just only assume the hardware in the simulation, in the experimental part. the thing is, we have the first assumption when we do the research or study of in the paper level, in the research level, we only assume, okay, our channel, our physical layer is like this, like for example, like 0.11p, right? So always like 5G is cellular. So we first assume the physical layer, but we not constrain our technology to that physical communication technology, because we always want to design some new algorithm to more common physical layer technologies. Okay, so that's all my. No, there are more questions. Yes, I didn't. I saw there's a question from Saliza. Saliza, I'm not sure. Sorry, I'm not sure I pronounce your name right. And in your paper of UAV path planning, do you consider the dynamic obstacles? Yes, we have in the PowerPoint slides. I just list one path planning paper, but we have the experience of doing the UAV path planning about more than 10 years, on my team. And we also consider the dynamic obstacles like other UAVs and other aircrafts, right? So how to use the UAV. And currently we're also working on another paper and about how to use the collaborative grouping clustered UAVs and by doing the path planning, how they can avoid the dynamic obstacles. And yeah, and I think this last question from Nordin. Yeah, he said in Malaysia 5G is still in pilot test. Can you please share your experience using 5G network and the challenge of 5G deployment? Okay, this is quite good question because it like impact all of us. For 5G network is first expensive. During the start of my talk, I said the 5G, for example, in China, it needs 20 millions of 5G base stations to realize the 5G connectivity everywhere in China. But which I mean everywhere is only outdoor, right? But if we include indoor, we need more and more 5G base stations. So it's very expensive. If one country want to deploy 5G network like in this land, right, it will cost lots of money for the infrastructure. And currently in China, some of base stations are not real 5G. They upgrade the 4G LTE base stations and to upgrade the core network by borrowing the 5G technology. And after release 13 and release 16, right, the future base station we built in China are, I think, going to be the real 5G. And for the real 5G, limited by the communication range of the real 5G, we're going to need more and more base stations. So for every countries, every government, they have to spend lots of money, right? In this case, so I think that the expense, I mean the pricing for the customer and why customer want 5G rather than 4G. I mean 5G is basically designed for the industry informatization, not for the standard customer, because for the most bandwidth consumed application for the standard customer like us, only the real-time streaming, real-time video streaming. But 4G can fully fulfill the demand of the real-time real-time video streaming. But why we need 5G? More expensive, right? But this is the why customer buy the 5G. It's another challenge. Yeah. But anyway, all the governments want to deploy 5G because I believe they want create more job positions, right? Create more working positions to their employees, to create more opportunities. And the next question is I understand the 5G provide high data traffic, yes, and high QoS, yes, and by integrating into the existing infrastructure. How about it makes a different spectrum of like lower band and plus 5G to serve in IIoT, isn't it? To be honest, I'm not expert in lower pan or lower WAN, and also I'm not an expert in MAC layer or physics layer. But I believe once I read a paper about the mixed spectrums, white paper about the mixed spectrum of the LTE V2X, LTE-V, and the DSRC, right? It's a white paper provided by 5G AA. It's an automobile standardization group association, yeah, in Europe. Yeah, they said they have a white paper discuss and show the information how to mix the different spectrums for the vehicular networks for DSRC and LTE. I believe if it works, the LoRaWAN plus 5G can be another solution. Yeah, because 5G is actually 5G energy consumed, right? And for the IIoT, as you said, and also for the agriculture, as previous gentleman asked it, LoRaWAN they consume lower power, so I believe it can be a good solution, a good promising solution for the industrial IoT. Yeah. Okay.
Okay.
Thank you, everyone.
Okay, thank you, Dr. Zhao. Ladies and gentlemen, with that concludes our webinar today. On behalf of organizer, I would like to take this opportunity to once again thank Associate Professor Dr. Zhao Liang as the speaker, as well as the audience for attending and participating in this talk. Thank you once again and have a good day.
Thank you, everyone. Thank you, Ben. Thank you.